Thank you, Arash. So to start off with, I'm going to show the presentation. In doing so, we're going to be talking about, as Arash mentioned, the Pypeline and Alpyne libraries. And these are two different libraries which allow you to incorporate Python into your simulation modeling workflow. So just for some context to get started, I will first go over some background information. So in recent years, Python has kind of overtaken the scene in terms of popularity. And if you look at multiple online indexes that score languages based on a multitude of different factors, such as available jobs and Reddit and Twitter posts and other sorts of user interaction, Python has ranked 1 or 2, right next to Java. And so it's easy to see why, considering multiple different factors, such as its simple syntax, which is not only good for beginners as an introductory, but also it makes for the language to have some more elegant syntax. And its integration with more lower level libraries like C or C++ means that you can take advantage of the speed that comes from having libraries programmed in that language. And then there's also a large library covering everything from data science to AI to enterprise and web development. So a multitude of large companies like Reddit, Instagram, Dropbox, and Uber all have their backends in Python. So with that, it might be desirable to have simulation into your workflows. And so with that comes a wide range of possibilities, such as being able to run experiments using optimization within a simulation, and training and testing RL algorithms, and enhancing your models with data visualization libraries. Now, obviously, these aren't unique to Python. These are all things that you can currently do within Java, but for those that are more familiar with Python, and also where it's more practical, where you might already have scripts written in Python, it would be much more convenient to simply be able to do that within your AnyLogic model. So currently, there are plans to allow all these different features, either partially now and also in the future. So the Cloud API currently allows you to run simple traditional experiments, which allow you to get inputs and outputs within a Python API. And there are plans in the near future for it to have an interactive API, so you could do RL training. And as you might have heard, or as you will hear about in this conference, AnyLogic 9 will have Python integration built within it, so you could directly use Python code while building your simulation models. So then why do we need the Alpyne and Pypeline libraries? Well, for number one, they're both available now, and they're also free to use, and they're open source, so you can modify them if you want. And so this makes it desirable not only for students and researchers, but also professionals who are looking for an easy way to get started, maybe doing different tests or experiments or making proof of concepts. So just for some more background, there are two different libraries because there's kind of two different ways that you can incorporate Python within your modeling workflow. So one is where you're calling Python within a running AnyLogic model, where you're defining some logic or calling on some external Python scripts from as part of your model logic. And this is what the Pypeline library is generally used for. And then there's also, if you want to, after you're done building the model, if you want to be able to control it using Python. So this is on the implementation side. And so this is what the Alpyne library is for. So I'm going to start with going over the Alpyne library and showing some examples of that. And then later on, I'll move on to showing Pypeline. So Alpyne is a Python library. So it's you interact with it within a native Python environment. And it allows any model exported from the RL experiment to be interactively run within your local environment. Now, before I expand upon what that exactly means, just a bit of cautionary warnings is that Alpyne as a whole is meant for very technical users who are looking to manually train RL agents. And so this is outside of the AnyLogic ecosystem. This is kind of after the model development has finished and you're wanting to now move to a Python environment entirely. So it's now outside of the AnyLogic ecosystem. Okay, so in explaining what Alpyne is, it helps for some background first. And so if for those who aren't familiar, Alpyne makes use of the RL experiment, which was added in AnyLogic 8.7. And I'll take the next few minutes to explain what the RL experiment is and reinforcement learning more generally. And I'll start off from some familiar concepts that are that a simulation modeling audience understands already and build onto that. And so in these analogies that I draw, it's not meant to draw, they're not meant to compare one for the other, but just kind of a foothold for the knowledge. So when you typically have a traditional experiment, you'll have a model, and that model will have some inputs or parameters, and then some outputs and some data sets. So you'll run experiments where you'll start a simulation run, and you'll have that experiment run the model and its internal logic, which to the experiment's perspective is a black box, as you see here. And then it runs till the end, and then you can retrieve some outputs from that. And through doing that one or more times, you can extrapolate some useful information from that. So in contrast with when it comes to reinforcement learning, the interaction is happening within a simulation model. So the interaction, you have to kind of take away that the experiment using it as a black box. So with reinforcement learning, you're delegating some decisions, which we call actions, that are happening throughout the model's execution to the AI algorithms. And so this is triggered via a function, which is part of the experiment called take action. So what happens is that similar to traditional experiments, at the start, you'll set what's called a configuration. And as I'll show in a little bit, the configuration is kind of a layer on top of your parameters. And it serves as a way to expose just a limited amount of the parameters that you want the RL agent to be able to experiment with. And so at various points within the model that you define, which could be either time-based or condition-based, the model will call that take action function. And when that happens, the model will pause itself. And in these moments, it allows an observation to be sent to the RL agent. And this observation consists of values which are relevant to the actions that you're delegating to that RL agent. And after the action is taken, the model is allowed to continue throughout its normal logic. And this goes on until either the next step or the next iteration, and then it continues until it hits some terminal or done condition. And these are either usually time or date based, or it could be condition based. Now the RL experiment was added in AnyLogic 8.7 as a way to kind of create a standard generic interface which any reinforcement learning platform could make use of. And so similar to a custom experiment, it doesn't have any graphical interface. It's just meant as for the end users to be able to fill out the relevant fields, and then you can utilize your model in whatever platform you're exporting it to. So unlike the other experiment types, you can't run it within AnyLogic itself because AnyLogic doesn't come with those RL algorithms. And so there are sections where you define the data elements, which consist of the observation, action, and configuration, and then also set the terminal conditions. And then along with that is code fields where you can apply or utilize those data fields. So with that, I'm going to make this a little bit more concrete by using an example that will both introduce reinforcement learning a little bit more and also the library itself. So we're going to start off with a simple warehouse that holds a limited amount of product, which we'll call stock. And so it's depleted at a certain rate, which is controlled by exogenous factors that we don't know and we can't predict. It just fluctuates over time. However, there is we're replenished by a daily rate of new stock, which we can update once a month. So in other words, every month we could choose what we want our daily order rate to be, and that is what we'll be refilled with. And here we say that our overall goal is to maintain a 50% capacity. And so that's to kind of account for those fluctuations in case it gets, we reach a period where there's a higher amount of demand. So if we were to try to solve this problem, there's 3 general ways that we might go about doing that. So one is we can hire a human worker, and this human worker will come in once a month, and they'll look at things like how much product is currently in stock, what the recent demand has been, and also what our previous order rate was. And from this, they'll figure out what our new stock should be, or new arrival rate should be. Another thing that we could do is we could devise some heuristic or an algorithm to be able to determine what this new stock should be. And this could be relatively simple if we have a straightforward inventory policy, but it will overall be limited in scope because it doesn't consider the more complexities that we want to add into this algorithm, the longer and more complex our code base is going to be. And the other issue is that it might not account for edge cases or other scenarios that wasn't thought of in advance. And the third method we might do is use a reinforcement learning policy. And to do this, we need a simulation model of our warehouse. And then we can train it on hundreds, thousands, or tens of thousands of episodes. And then it can kind of see a full range of different possibilities, and then get some feedback on its actions. And so from this, it will be able to learn a control policy, which hopefully can optimally keep our goal at the 50% capacity. Fortunately, there's a example model that comes with AnyLogic that fits this description almost perfectly, and it's the stock management game. So this is one of the models that comes with every install of AnyLogic, and it's been modified slightly to accommodate Alpyne. So starting off, I will just give point out a few things, and then I'll show a quick demo of it. So in this model, one thing which I didn't account for or didn't mention before is that there's this concept of lag. And so what the lag is that for any given order rate that we set, for example, let's say we want to set the order rate to 15 per day, the lag is how many days it takes to get that full order, and it's divided evenly. So if here we have a 3-day lag, so our 15 order rate would be divided into 3, or we'd end up getting 5 per day. And this is significant because if we wanted to, similar to how this end user that's playing with this model can try to control the arrival rate of the order rate of new product with different amounts of lag, and they can kind of learn from that. Maybe we want the RL agent to be able to do that as well. You can also notice that under the parameter section, we have 2 other parameters which weren't exposed to the end user through this interface. One is the execution mode, which in this case, if we're running the simulation experiment, we want it to be user controlled, but when we export it later, we'll want it to be AI controlled. And then also an amount which limits the upper limit to how much we could hold. And so if we try to get any more than that, that amount will get wasted. And so in this case, this is a fixed amount for every simulation run. So if I switch over to AnyLogic really quickly, I will show you a quick demo of the model just so things are a little bit more familiar. And just to simplify things, I will set the lag just to be 1 day. So if I set the order rate to be 15, I'll get 15 per day. Now you can see that there's an event here. And in this case, every 30 days, it pauses the model. And as the human controller, I could say what I want the order rate to be. So in this case, I might keep it at 25. And you can see that the amount of stock that we have increases. And if I change the order rate, that will obviously also increase as well. And so while this is happening, there's a demand which is not known to me, but is slowly increasing, fluctuating randomly. And once we hit that 10,000 mark, now we have product wasted. And so if we wanted to try to achieve that 50% or close to 50%, it's a matter of kind of considering a multitude of different factors. And so this model will run in this kind of stepwise mode where every 30 days you can make a decision, and it will keep doing this for the model is set up currently to run for 2 years. And so once it gets to the 2-year mark, the model will end itself, and then that's considered the end of this simulation run or episode if we were doing RL training. So with that, back to here. And so I will kind of speak more to the nuances that in just a moment. Actually, yes. So if we want to train the RL agent with that, we'll need to set up the RL experiment. And to do that, we have, like I said, a multitude of different fields. So one is the configuration, and this is what we want to start the episodes with, and what we want to be able to expose to the RL agent as options to control. So in this case, we're just exposing the amount of lag. And here in this code field, this will get fired at the start of each episode. And so we could do things like validating the input that's sent to make sure it's greater than or equal to 1, in addition to hard coding some other parameters that we want each training episode to start with. We also have the observation, which is going to be those values which we think is most pertinent to the AI to take the best action. So in this case, it's concepts like the current amount of stock, the last 3 stock amounts that we had, the last 3 days, the last order rate, and the model time. And then in the action field is what we want the order rate to set. And so with these conditions filled out in conjunction with more common sections like the model time, so here we're still running it for 2 years, and setting the random number generator seed, the model is all set up to go. And it also needed that trigger take action function. So if I go into the model and look at this action event, you could see that based on that one parameter, I call the take action function. So this is what will trigger that kind of loop to take place throughout the model. And this will happen at the same rate in this case as the user was controlling the model. So when it comes to using it in Alpyne, just to give you kind of a high-level workflow before getting into it. So once we've kind of set up the model and it's fully RL ready, we can export it using the available options. And this is available to anybody regardless of your AnyLogic edition, so even to PLE users. And so it exports as a zip. And inside of our Python script, what we'll do is we'll create what's called the Alpyne client object and pass in our exported model. And from that, we can create a multitude of different model runs and interact with each one of them in parallel if we wanted to. And each one is its own self-contained environment, so it could be reset and reused for as many episodes as we need to train for. And this is a similar structure as you'll see as how the Cloud API works. And this is intentional just to ease the transition in case you're ever wanting to scale up your experiments from Alpyne, which is again on just your local environment, to one which can handle more intensive trainings, which will be the Cloud API once that interactive API is ready. So a few quick mentions, just a preview of what we'll be talking about next. So of course, the next kind of portion of this will be going over 4 different scripts, which kind of build on themselves in terms of complexity. The first 3 that I'll show are not really practical, but are simplistic just to explain the kind of workflow of the how the code looks and how you can interact with it and how the general usage of the library is. So we'll start off with just a single run and predefined actions. So what this means is that we'll just use a fixed action on each step. And then I'll show about how you can parallelize runs. And again, it'll still use those predefined actions, and it will manually be implemented, which is to say we'll have to check what the state of each run is before taking an action. And then there are a few classes that are provided with the Alpyne library which help automate this process. So the 3rd script will show an automated implementation of this, and the 4th one is we'll show an RL example, how you can use Alpyne for RL training in any sort of RL library. So naturally, of course, we're now kind of leaving the safety of the AnyLogic ecosystem with its beautiful mantra of less code equals better. And now we're just diving into pure code. So that's just a warning going forth. So this is the RL side of things. And so with that, I will look at the first script. So here we're inside of PyCharm, which is a Python development environment. I have my different Python scripts. And so here what I'm doing is I'm creating that client object and passing the path to my model jar. There's a feature called blocking, which will, so there are a variety of time-consuming tasks. So if you have a very intensive model, taking actions in the model will start resuming the simulation, which for heavy-duty models will take some time for it to process. So what setting this blocking equals true will do will provide a way where you don't have to kind of manually pull the server. It will just hang the current thread until any time-consuming tasks are finished. So at the start, there are various different template objects available in this client object. And so this just prints them out just for our reference. So this will show you kind of what the default values are and what the names are. And then we create a new configuration object. So this is our RL inputs. And then here you can see that we take that acquisition lag days, which I defined in the configuration section of the RL experiment, and so we want set the value that we want to run the model with, in addition to the engine seed. So this is what we want to, the conditions that we want to run the first episode with in this case. Then we're able to create a new reinforcement learning experiment, passing in that configuration, and then starting it. And then we enter this main loop here. So while that simulation model is not in a terminal state, which is to say our stop conditions haven't been met yet, we check the current status of the engine and also some kind of debugging information and print that out. And then we get the observation that gets printed out. And then we use an action template, which is kind of an empty version of our action object, which I had set up the definition for in that RL experiment. And then we set that equal to a fixed value, which is just 25. And then we command the simulation model to take that action, and then it continues on to the next step. This then jumps back up, and then it continues doing this until the model is finished. And then at the very end, what we're able to do is we're able to get the outputs. And so what this will do is it will extract all of the analysis objects, which were inside of our top level agent, which is main, and then output it inside of our Python environment so that we could access it. Now, in this case, I inserted a variety of different analysis objects, different data sets to keep track of various elements in the model. So then I use the matplotlib library here to kind of plot all that out so you could see that inside of Python. So I will go ahead and run this. And then what will happen is that it will, so there's when you install this library, it comes equipped with an application which allows you to, which is what it kind of is the back end of how this works. And it appears to be not cooperating. So with that, we will give it a second to think about its actions, and I'll move on to the next example. So in this one, we're wanting to run multiple simulation runs in parallel. And so Alpyne is able to allow you to do this without any issue, without any extra code on your Python side, and it is able to handle that on the application side. And so this is where another interesting feature of it comes in. So as with before, we're creating our default inputs. We're setting that lag date to be 1, same as before. But now what we're doing is we have this incrementer object. So this is part of a standard Python library, which each time you call it, it starts at 1 and then steps up by 1. So here we're setting the engine seed to a callable value, or essentially a function. And what the Alpyne library allows you to do is pass in values as callables, and every time every time that value is needed, it automatically queries and updates for the next one. So then what we could do is we can create 4 reinforcement learning experiments, passing in that one configuration object, and each one will have a different but known seed. And then this operates similarly to the other one, the simple example. So while they're not, well, at least one of them is still operating, it loops over them. It checks if the model is currently in a pause state. So when the model is paused, that means it's ready for observations to be taken or actions to be taken. And so then it again gets that fixed order rate, and at the very end, it gets all the outputs and then adds that to a different matplotlib plot. And so when it's able to run, which this is the nature of doing things live, and when your computer is not working as intended. Okay, so then in that case, we will move on, but it is a very cool plot, and I recommend at the end when I show the download link at the GitHub that everybody go and try that out. So as I was saying before, there's a few base or abstract classes built in to the library, which allow you to greatly simplify things. So in this case, I've condensed all of that code that I had previously just showed down to a matter of 3 lines, at least in this main execution part of the code. And that's because up here at the very top, I have defined a class which extends the base multi-run, which belongs to the Alpyne library. So this base multi-run class is abstract, which is to say that it comes with some empty functions that you need to define. And then once you do that, it can handle the core logic. So if I scroll down to kind of the routine logic, so here there's this run method, and this run method is where the kind of routine logic is. So this is what the type of logic that will apply to any model that you want to run, multiple parallel runs with. And so because a lot of this is routine and common regardless of the model, it can be, pre-written like this. And then all you need to do as the end user is fill in the parts that are very specific to your individual model. So in this case, that's querying what the configuration should be for any new run, and then also for filling out an action template based on an observation. And so this could be used either as part of a manual RL solution or to test an RL algorithm. And then there's also additional callbacks where you can implement any other logic. So that's the kind of abstract version of the class. In the implementation version, which is for this specific example, so this will look familiar. Here I'm in this get configuration, which I've overridden, setting that lag days to 1. Doesn't have to be, but that's kind of a simple use case. And then again, I have a counter that I had created at the initialization of the object, and now I'm querying the next value. Similarly with the actions, just using a fixed action. And then at the end, there's an overriding the episode finish method to keep track of the outputs. And so that's how this is able to be condensed in such a way. And I will try to be optimistic and see if that will run, but I guess not. Okay, so then moving on to our last and most interesting example. So there's one other abstract class, and if I scroll down to that here, and it's called base Alpyne environment. So there's a popular library called Gym by OpenAI, and that the Gym library has kind of standardized RL environments in a way that makes it very easy to have any sort of environment that you want to train an RL agent in, and it comes with some standard functions that can be used by common libraries like TensorFlow or as you'll see, stable baselines or PyTorch or anything else. So this base Alpyne environment extends that Gym environment, so it's a custom Gym environment. And so it comes with the functions that are required as part of this interface, this Gym interface. And just like the other abstract class, there are a few abstract methods that can't be automated by kind of me as the developer. It's kind of specific to your model and your use case. So these are made abstract so that you can fill them out. And it is for defining your observation space, so how many values and what are the dimensions of them, and then also converting that observation object to one which a common reinforcement learning library can understand. And the same also applies for the action space as well, and converting the action, which is a numerical Python, traditional Python-based type, and converting it to an action object which Alpyne can understand. And then also a method to calculate that reward. And then there are some methods here where most of that other logic is automated. So as a result of that, here we have our custom stock game environment. And so in this case, the decision is made that a lot of the values that I had sent as part of that observation definition in the RL experiment were unnecessary. So this observation is just going to consist of a subset of those. And then the order rate is going to be a value between 0 and 50. And then there's a reward function that's defined based on the current stock amount, giving a higher reward if it's closer to 50%. So in the implementation of the class, it is able to convert, defines the action in the observation space. And here we extract the two relevant values from the observation object, and we convert it to the NumPy array, which is something that TensorFlow or stable baselines is able to understand. Similarly, the RL libraries are going to send back an action, which is a scalar value from 0 to 50. And so for Alpyne to be able to process that, it needs to be returned as an action object. So we define the order rate, which is the name of that data field that we had defined, and the RL experiment, and we set it to be, that value. And so what that will look like at the end is that we can, again, this is kind of should look familiar, is that we create an initial configuration. We pass that to create a new model run, and then we can wrap it in our custom gym environment. So at this point, once we've done this wrapping process, we can now utilize it in any sort of traditional Python-based RL library. So in this case, stable baselines is used to train the environment for 500,000 time steps. And then at the end, it's able to save that policy to a zip file, which we can then either utilize within here, still within this Alpyne environment to kind of see how well it performs, or we can import it back into AnyLogic to use in a visual way. And once again, I will try to see if this will run, but we shall see. So with that, those are the 4 example scripts, and I'll switch back to PowerPoint to go over a few other things. So kind of summarizing and also adding some additional remarks. So with this Alpyne library, you're able to train your models in a Python-based environment. And that's kind of what the intention of the Alpyne libraries for, is allowing you to utilize the RL experiment in your own local environment. And so naturally, as a result of that, it's intended for very technical users who are both familiar with Python and RL libraries. And so as it's through this RL experiment, that's the only way of communicating with your model. So it's not meant to be a replacement for any other AnyLogic experiments. And you wouldn't want to do it anyway because your execution is just based on your local environment. And so it's based on, it'll be constrained by your hardware. And so if you're looking for more scalable solutions, in the very near future, the cloud will have an interactive API, which allows you to do the same sort of thing, but offloading the computational complexity to the cloud, or if you own the private cloud, that as well. And then for automated RL solutions, so if you're not interested in the technology side of things or the coding side of things, we have our Bonsai and Pypeline platforms. So with that, that now brings me to the Pypeline side of things. So Pypeline, in contrast to Alpyne, is a custom add-on library for AnyLogic that allows you to connect to and communicate with Python from within your AnyLogic model. So to elaborate a little bit more on that. So for those that don't know, you can take any AnyLogic model where you have any level of complexity in your agents and bundle them into a library, which you can then add back into your AnyLogic environment. And the benefit of this is that it allows not only you to reutilize these assets that you've created, but also for you to distribute it to others if they wanted to use it as part of their processes. So that's exactly what Pypeline is. So it's this add-on library, which you can add to your AnyLogic environment. And it comes with one object called PyCommunicator, which is how you interact with Python in your simulation model. So when I say connecting to local installation of Python, what I mean is that Pypeline does not ship with any specific version of Python. And this was very much intentional so that regardless of what version of Python that you use, or if you have a specific virtual environment that you want to make use of, you can specify that from within the properties of this PyCommunicator object. So when it comes to actually communicating with that version of Python, there's a series of different functions. And so there are some methods for either running arbitrary sets of Python code, or such as like imports or setting values. It's set up as an interactive environment, or you can run standalone Python files if you want to just retrieve the values and maybe pass some arguments. And then there are additionally some other functions that allow you to convert to and from JSON. So JSON is an intermediary language that's used between AnyLogic and Python for data passing. And it stands for JavaScript object notation. It's a common format used on the web. And it allows you to format data in such a way that you can have simple values such as strings or numbers or Booleans, or you can build that up into array lists or dictionaries, any sort of like multi-dimensional objects that fit whatever data that you're needing to describe. And so these to and from JSON functions let you convert different attributes of your model into values that Python can process. Another feature that you'll see in the coming minutes of this library is the ability to locally import any Python files that you from within your AnyLogic model. So as you could see from this example here, the way that you execute Python code from inside of AnyLogic is through strings, so through Java strings. As you might be able to imagine, that there's no error checking with that. So what this allows you to do is you can offload all of your Python code to standalone files and then minimize the amount of Python code that's needed in your AnyLogic environment. And the other benefit of that is that you can kind of test your Python code in a native Python environment and then utilize it from within AnyLogic with less concern for whether it'll run. So in terms of use cases for why you would want to be able to use this library, one is that if you have existing algorithms and it's infeasible to convert all of that into Java, you could use this library to make use of those. Additionally, there are different data visualization libraries which could allow you to enhance your model even further. And also, if you're wanting to re-import machine learning models, which includes reinforcement learning models, back into your simulation model to use it as a test bed, you could do that as well. So just a few examples of that. So in this first example, we have a traveling salesman example. So within this model, I have a Python file, which if I actually go back to that and I open up my model folder and then check on the Python file itself, you'll be able to see that again, this is a standalone Python file. It comes with a class that implements a solver using the OR tools library from Google. So this logic for how to use this solver is kind of offset to this Python file. And then within our AnyLogic environment, we can call that Python code through the PyCommunicator object through a series of imports and requests to convert from to JSON or to pass data to and from. And so what that ends up looking like is as follows. So here, this traveling salesman example, we have a truck that belongs to a facility at Kansas City, and it is tasked with visiting 3 or more locations, and it has to both starts and stops, finishes its route at Kansas City, and the optimization part, which is happening during the simulation run, is what the shortest route to take is. So whenever it returns back to Kansas City and gets a new route, it requeries Python for the order of those locations of where it should visit. As a secondary example, we also have this Lorenz weather model. So this is a system dynamics model, which is showing kind of a chaotic system, but in a deterministic way. And you can see in the base AnyLogic model, we have some 2D graphs. And then we're making use of an interactive matplotlib graph to be able to plot this in an interactive 3D graph. So we can, pan around, and if we were to change values and then check back on the graph, you could see that it, is able to update live. And the other thing that this model shows is there's a parameter variation experiment. So here we've kind of varied some of the inputs, and then when we run that without any extra code, the model is able to show that in parallel with one another. And so we can play around with each of these three individually if we wanted to. And the last model that I will show for here is a simple hospital one. So in this case, this is the kind of third case that I was talking about. So here we have two different data sets that we train some machine learning models on. So one determines the arrival rate of patients. So it uses past data to predict what the next 4 hours of arrival rate should be. And then we also have a data set that we trained on to determine what the patient's length of stay should be. So the questioning factor that we have here is how large should our hospital should be? How many beds should we have? So we run the model. What it's going to do is import the TensorFlow libraries, which usually takes 2 to 5 seconds, and the model's able to start. And so naturally, as a result of using specific Python libraries, the requirement is that, to be able to run these models, you need to have these libraries installed in whatever version of Python that you're utilizing. So in this case, you can see that there's little brain icons to indicate, where these, where Python is being queried. And so every time, for every 4 hours, and also whenever a new patient comes in, it is delayed. So we have some graphs here showing what the fluctuation of arrival rates are, in addition to the number of patients that are queuing or staying. You can see that this is slowly increasing, so we might up this level to kind of, offset that, and then some histograms that show you the predicted times and then overall times as well. So here we're able to utilize these neural networks within a AnyLogic environment with minimal code. And some final remarks on this. So despite all these cool features, Python in this case is not meant as a replacement for Java coding and AnyLogic models. The kind of trade-off here is speed-based. So kind of native, there is some overhead. So the native solutions will almost always be faster. So and using these libraries are just kind of a supplement on top of what you're already kind of doing within AnyLogic. And just to kind of reiterate that if you're wanting to use a library for training RL agents, that'd be what Alpyne is for, in addition to our other partners in the AnyLogic Cloud API. So resources. So both libraries are available on GitHub. And so there are short URLs here that you can access. Both of them come with instructions on how to download. In terms of, for the Alpyne library, installation happens through Python's built-in package manager pip. So there's a link to instructions, and there's also some API docs and example models, including the scripts that I showed today. And then for Pypeline, there's also a wiki with kind of detailed usage and troubleshooting. in addition to the library jar file that you need to utilize within your that you need to import into your AnyLogic environment. And we also had a webinar on Pypeline that is available from our YouTube page. All right, so with that, I believe we are looking into Q&As. I'll leave this here. So in terms of questions, so there's an example model. So somebody asked, there's an example model in the software about the beer distribution game. Do you have any model to show that famous beer game of supply chain? I'm not sure if this is asking kind of generally if we have a model, because we do have the beer distribution game. I started to implement a solution for that using Alpyne, which I'll probably eventually upload, but couldn't get decent enough training from it, just due to not being even remotely experienced in RL. Number 2, does multi in your Python code mean parallel training of RL? Yes, so the Alpyne, so I guess for both. So for Alpyne, I had parallel runs going. Actually, if I go back into the PyCharm, so if I were to show my screen again here. So here, if you're able to see my screen, is the training script in Alpyne comes with, you could vectorize that stock game environment class that I had created natively using stable baselines in this case. So the trainings are able to happen in parallel, whatever parallel means for whatever library you're using. So in terms of, from Alpyne's perspective, yes to all sorts of parallel variations, at least the definitions. It just depends on whatever RL library that you're using. For Pypeline, the models that I was showing obviously weren't training in RL, but they were all operating, all the Python scripts were happening in parallel. Another person asked, can we use Alpyne without RL experiment? No. So Alpyne is completely centered around the RL experiment. You have to define your interface through that. But the good part about that is the experiment is available in AnyLogic's PLE edition, but limitations of PLE still apply. So if you have a PLE model that uses the material handling library, I believe, you're limited to 1 hour of simulation execution time. So the same, if you go on to the anylogic.com/downloads, the limitations that you see there still apply for the models that you export from the RL experiment. Another question was, can we use this Python connector and AnyLogic extension under ALX? So no, as of right now, well, as of the last time I checked personally, so I don't know if anything's changed as far as I know. ALX doesn't support custom AnyLogic libraries to be added to its kind of internal AnyLogic. So you cannot currently use Pypeline for that. If you did, I would suggest making a request for support so that they're aware of the interest in that. The next question, can this modeling be used for calculating quantity of stock owned in an investment portfolio? So that, I mean, in general, yes. I mean, you could, I mean, I'm not too familiar with that concept as well, but given all of AnyLogic's capabilities, I don't see why. That's kind of more of a broadly, you know, modeling-based question as opposed to what Alpyne or Pypeline can do. If you, you know, have Python libraries that you want to use or that you're more familiar with to do that sort of thing, you can do that as well. So with that, I think that is all the questions that we had. So thank you very much again. Again, if you want some more information on either of the two libraries, there are the two GitHub links. So git.io/Alpyne or git.io/al_pi. And with that, thank you very much for listening.